Hi there. Today we're going to explore the theory of relativity, but not through formulas or complicated jargon. We'll do it slowly, clearly, using simple examples step by step. We'll start with a moving train, a flashlight, a bouncing ball. We'll look at coffee cups and twin brothers, at clocks and satellites, and we'll ask questions that seem naive, but lead somewhere deep. Because relativity isn't about abstract physics, it's about how time and space themselves behave. And, surprisingly, it all begins with something as ordinary as standing on a platform and watching a train go by. Let's begin. Chapter 1. What does it mean to move? When we say the train is moving, we're confident we know what that means. Here are the tracks. There it is, the train. And it's moving. All clear. But let's pause. Literally, stand still. On the platform. No rush. You're standing. The train rushes past, whistling, roaring, thundering ahead. Obviously, the train is moving, and you're not. Now imagine, you're inside. In a soft seat across from you, someone with a newspaper between you, a small table with a cup of coffee. And if someone asked, "Is the train moving?" you might be surprised. "No," you'd say. "Nothing is moving. Everything is calm. Even the coffee doesn't ripple." So who's right? Both are. Because motion is not something that exists by itself. It's a comparison between you and something else. Relative to the platform, the train is racing. Relative to your seat, the cup is still. There's no such thing as absolute stillness or absolute motion. There is only motion relative to something. That's the first strange thing. A strangeness so familiar we no longer notice how strange it is. Let's take another example to make it clearer. Imagine a river. Wide, calm, with a gentle current. On it, a raft. On the raft, a man sitting and reading. The raft drifts slowly downstream. Now imagine someone on the shore. He's standing and watching. He sees the raft moving and says, "It's floating." All logical. Now imagine a third person. He's paddling beside the raft at exactly the same speed. He rows gently, steadily, and his boat stays perfectly aligned with the raft. He looks at the reader and sees that he's not moving, as if frozen next to him in a motionless world. So who's telling the truth? Both. Because motion is not a thing. It's not a label you can stick on an object. It's a relationship. One thing relative to another. To the person on the shore, the raft is moving. To the one beside it, still. And both are absolutely right in what they observe. Chapter 2. The ball and the flashlight. Imagine you're back on the train. This time, it's an experiment. You take a ball and throw it straight up. It rises and falls right back into your hand. It all makes sense. It's simple, but someone standing on the platform sees something else. To them, the ball travels in an arc, upward and slightly forward, because while the ball is in the air, the train is still moving, and the ball moves with it. So, who's wrong? No one. Each person has their own frame of reference. Each has their own version of truth. And physics says both are equally valid. Now let's talk about the flashlight. You're sitting in the train and you switch it on. A beam of light shoots forward. So what? You say. It's just light. But now imagine someone is standing on the platform watching this. They see the beam too. And here's the strange part. It moves at the exact same speed for them as it does for you. Not faster, not slower. even though the train is moving, even though you are moving. The light still travels at the same speed for everyone. And this is where the real magic begins. Let's imagine a wide, empty avenue. Early morning. No one around. Someone glides down the avenue on rollerblades, smooth and effortless. In their hand, a tennis ball. They're skating at exactly 10 kilometers per hour. And then they throw the ball forward at 20 kilometers per hour, relative to themselves. What does a bystander see? They see the ball flying forward at 30 kilometers per hour, 10 from the skating, 20 from the throw. The speeds add up, just like in real life. It all makes sense. Now the same person is skating again, but this time, instead of throwing a ball, they switch on a flashlight. The beam of light shoots ahead. What does the bystander see? They see the light too. But here's what's strange. It's not traveling at light speed plus 10. It's just the speed of light. The speeds didn't add. Light didn't gain a single centimeter per second. It's as if it simply refuses to play by those rules. Why? Chapter 3. Something has to give. If light doesn't change its speed and you are moving, then to keep that speed constant, something else must change, and that something turns out to be attention, time. Yes, time begins to adjust. It stretches a little. It slows down just a bit. Still not frightening, but let's take a closer look. Chapter 4. The Light Clock. Let's imagine a simple clock. Very simple. It's made of two mirrors, one above the other, and a beam of light bouncing between them. Up, down, down. Each full bounce, there and back, is one tick. Light moves fast, very fast, but not infinitely fast. It still takes time to travel from one mirror to the other. And that time is what we call a tick. Now imagine the clock is standing still. The light goes straight up and straight down, precisely, rhythmically, like a metronome. Tick, tick, tick. Now take this exact clock and place it on a moving train. What happens? For someone inside the train, nothing changes. The light goes up and down, tick, tick. But for someone on the platform, things look quite different. They see the train moving forward, which means the mirrors are moving too. And the light, it's still bouncing between the mirrors, but now it travels diagonally, up and slightly forward, down and slightly forward again. So, the light's path is longer, but the speed of light hasn't changed, which means it must take more time to complete the journey. What does that mean? To the person on the platform, the clock inside the train ticks more slowly. Tick, tick, tick. Chapter 5. So, who's right? So then, to the observer on the platform, the clock on the train ticks more slowly. We've already seen why. The light travels a longer path, and its speed doesn't change. So each tick takes more time, which means time itself has slowed down. But now let's ask another question. Does the passenger on the train notice this slowing of time? The answer is no, not at all. Because for them, everything moves at the normal rhythm. They don't see their clock lagging. They don't feel their heart beating any slower. They don't notice their thoughts drifting more slowly. Why? Because everything around them, the clock, the pulse, the conversation, even the firing speed of their neurons, has also slowed down by exactly the same amount. To them, the world remains perfectly synchronized. If they put a kettle on in the train, it will boil at exactly the moment they expect. If they're watching a film, each frame will follow the next, just like always. Inside their frame of reference, nothing unusual is happening, but the observer on the platform sees something different. They look through the window, and if they could see clearly inside, they'd notice everything moving slower. Slower speech, slower gestures, slower blinking. But for the passenger, it's not slower. It's just normal life. This is one of the subtlest and most beautiful ideas in the theory of relativity. Time dilation is real, but it's locally invisible. You can't feel it inside your own system because you slow down completely, your entire being. And you always feel like you're in sync. It's as if you lived in a world where everything suddenly moved twice as slow, but so did your thoughts, your expectations, your calendar. You'd simply call it the new normal. And just like that, the world becomes a little more complex, a place with multiple rhythms, multiple personal times, each moving object living in its own tempo, and all of it coexists. No errors, no clashes, no noise. Somehow the universe knows how to make it all work. Chapter 6: The Twin Paradox. Now, let's imagine a little scenario, but not too far-fetched. What we're about to discuss has been calculated, tested, and, most surprisingly, confirmed. This is a thought experiment, a classic, a famous one, but it still works flawlessly. We have two brothers, twins, born on the same day at the same hour, just minutes apart. They've always been inseparable, eating together, running together, getting sick together. They share a common starting point, a shared past, a shared now. But one day, one of them, let's call him Alex, decides to stay on Earth. He writes a blog, grows basil, watches TV shows. The other, let's call him Max, becomes an astronaut. He boards a spaceship capable of flying at near light speed and sets off on a journey to a distant star and back. And so, the ship launches. Max is inside. Alex waves from the launch pad. That's it. Their paths diverge, not just in space, but in time. Max watches stars rushing past. He sees numbers ticking on the control panel. He reads, sleeps, thinks. In his spaceship, the clock ticks as usual. He notices nothing unusual. To him, 2 years pass. Then he returns. The ship re-enters Earth's atmosphere. A soft landing. The hatch opens. Max steps out. Alex runs toward him. But he's no longer a young man. He's middle-aged, with wrinkles at the corners of his eyes, with kids, nearly with grandkids. And Max has barely changed. How? While 10 years passed on Earth, only 2 years passed for Max. This is not a dream, not an illusion, not a glitch. This is a direct consequence of the special theory of relativity. How can we understand this? As Max sped through space at nearly the speed of light, his own time slowed down from the perspective of everyone who remained on Earth. For him, everything felt normal. But from our perspective, he was living in a slowed-down version of reality. And here's what's interesting. This isn't just a perspective or point of view. It's something you can measure. When the two people reunite, they can compare clocks. Real clocks. And if one of them spent years traveling at high speed, their clock will actually lag behind. Not because it broke, but because time itself flowed differently for them. That's how the universe works. Moving at speeds near the speed of light doesn't just change your direction, it changes how you exist within time. And this is the key to understanding one of the most paradoxical discoveries of the 20th century. Before Einstein, we believed that time was a universal rhythm, one big cosmic clock ticking the same for everyone. Turns out, it's not. Everyone has their own time. Each person lives inside their own flow. Most of the time, you don't notice. But if you move fast enough, it becomes obvious. In that sense, the twins aren't just a metaphor. They are you and me. You standing on the platform. Me in motion. We may think we live in the same world, but if you look closely, even our seconds tick differently. Chapter 7. Space Gave Way Too. By now, we've gotten used to the idea that time isn't absolute. It can stretch, it can slow down. But now it's time to talk about the other half of the duet, space. If time can adapt, then space is not far behind. Think for a moment. What does distance mean to us? A meter, a kilometer. It feels like something solid. Here's a ruler. Here's a tape measure. Here's the road from your house to the store. But relativity says even that meter is not universal. It can shrink. How is that possible? Let's go back to our cosmic twin, Max. Once again, he's in a spaceship, traveling at enormous speed. He's headed for a distant star, say 10 light years from Earth. From our perspective, standing on Earth, the star is far, very far. Even at near light speed, the round trip would take 20 years. But not for Max. From his perspective, everything is reversed. He's the one moving fast, which means everything else contracts along the direction of motion. And now the distance to that star, it's no longer 10 light years. It's less, much less, which is why he can fly there and back in just a few years by his own clock. Sounds strange, doesn't it? How can a distance shrink? Did the ruler get shorter? In a sense, yes. Not because someone bent it, but because the very concept of length depends on your frame of reference. Here's a simple image. Imagine a train rushing past a platform at tremendous speed. To someone standing still on the platform, the train appears shorter. It seems to contract in length. Not in height, not in width, just along the direction of motion. To the passengers inside, nothing has changed. Everything is familiar: seats, tables, newspapers, tea. But to the outside observer, the train is compressed. And this is not an illusion, not a trick of perspective. It's a real, measurable effect that appears at speeds close to the speed of light. If you could accelerate that train to 99.9% of light speed, its length would shrink by several times. From the point of view of someone watching from the outside. And here's what's important. This isn't distortion. It's not a mistake in perception. It's a coherent physical reality. Time slows down, space contracts, and all of this for one purpose: to keep the speed of light constant. And now we stand at the edge of a truly strange idea. Length, time, motion. They're all intertwined. You can't talk about one without affecting the others. You can't measure length without considering time. And you can't understand time without involving motion. The world we live in is no longer a rigid stage of clocks and rulers. It is a living fabric, one that bends, breathes, and responds. Chapter 8. Space and Time, Woven Together. And now we've arrived at the most surprising part, a conclusion that, at first glance, almost sounds philosophical. But in reality, it's pure physics. And astonishingly, it works. Einstein realized the problem is in how we think. We're used to dividing the world into two separate blocks: time, which moves forward; space, which we live in. They seemed different. One measured in seconds, the other in meters. One flows, the other just is. But it turns out they are not two separate things. They are one whole. Time and space are not just connected, they are stitched together, like thread and fabric, like vertical and horizontal, woven into a surface. Einstein gave this surface a name: space-time. This is where everything happens. Every event, every glance, every step has coordinates not just of where, but also of when. And together, that makes a point in space-time. Now imagine this fabric. When nothing rests on it, it lies flat, clean, smooth, undisturbed. Light travels through it in straight lines like across a ruler. Simple. But now introduce mass, any mass, a ball, a planet, a person, you. Mass doesn't just occupy space, it distorts the very fabric. Not maliciously, not intentionally, just by existing. Remember the trampoline analogy. If you place a heavy ball in the center, the surface bends. Now roll a smaller ball nearby. Its path curves, as if pulled toward the big one. But in reality, it's just rolling along a curved surface. That is gravity, not a force in the traditional sense, but the result of mass-altering geometry around itself. What we call falling is really just following a curved straight line. The shortest path, which in curved geometry happens to be not straight at all. A beam of light flying past the sun bends. Planets don't get pulled in. They move along geodesic paths carved into the fabric of space. Even you're not just standing on Earth. You're pressing your feet against a surface that curves downward beneath you. Everything with mass bends the fabric of space-time, and everything that moves within that curvature. This is gravity, not an invisible string, but a shape, a bend, a structure, and the more massive the object, the deeper the bend. The closer you get to the center, the slower time flows, and the harder it is to escape. And at some point, the curvature becomes so intense, it forms a pit, a real one, a black hole. But that we'll get to later. Chapter 9. So what is gravity, really? As kids, it all seemed simple. You throw a ball, it falls. A stone, same. An apple breaks off a branch, down it goes. You jump and come right back down. So, clearly, there must be a force. Gravity. It pulls. That's how we were taught to think. Gravity is a force that attracts. That's what the books say. That's how it was explained. But then Einstein came along and said, no, gravity isn't a force. At least, not in the way we imagined it. Wait, what? At first, it sounds like a provocation, but only until you see what it's replaced with. If you remove the idea of a force, what then makes the apple fall? Why do planets orbit? Why don't you float off into space? The answer is geometry. Remember, we've said space and time form a kind of fabric, and everything with mass bends this fabric. A planet, a star, even you, create a kind of dent, like a ball resting on a trampoline, and everything around it moves along these dents. Imagine rolling a small ball across the trampoline. It doesn't follow a straight line. It curves, it veers, drawn toward the heavy ball in the center. Not because someone's pulling it with a string, but because the path around it is already curved. That's how gravity works. It doesn't pull. It reshapes the surface you move along. What we call free fall isn't falling in the usual sense. It's simply moving in a straight line that, in curved space-time, isn't actually straight. Even light, which always takes the shortest possible route, bends when it passes near something massive. It curves, as if skimming around a funnel. That's exactly what astronomers observed in 1919, when starlight was deflected as it passed near the sun. It was the first direct confirmation of the idea that gravity is curvature, not force. Here's another example. You're standing still, just standing. Why aren't you falling through the floor? Because the floor resists? Technically, yes. But fundamentally, you wouldn't be falling if space itself weren't curved toward the center of the Earth. You're not just standing in place. You are, quite literally, trying to move along a curved path, and the floor is getting in your way. Now imagine the floor disappears. You don't soar upward like something tossed. You simply continue along the trajectory dictated by the shape of space-time, and that path leads you downward, toward the center of curvature. That is gravity, according to Einstein. Not attraction, but the influence of shape on motion. Mass bends space, and everything else just follows the geometry. And this is the moment where physics begins to sound almost like poetry. You're no longer a cog in a machine, pushed and pulled by invisible forces. You're part of a structure that gently tells you where to go. And if you feel weight, it's not because something pulls you down, but because you can't move freely in the curved world you live in. Chapter 10. A simple analogy. The stretched fabric. To really feel what Einstein meant, let's imagine something extremely simple. Not a formula, but a sheet of fabric. Large, elastic, smooth. Like a trampoline, but without springs, stretched tight in perfect silence. This sheet represents space-time. Now you walk up and place a heavy metal ball in the center. Not heavy in grams, heavy in meaning. It sinks into the fabric. No one is pulling it. It just exists, and that alone is enough to bend everything around it. Now you take a smaller, lighter ball, say a glass one, and gently roll it across the fabric. You don't push it toward the center. You just let it go straight. But it curves. Its path bends, as if something pulled it inward. But nothing did. It's simply rolling straight, in a space where straight is now curved. That is the metaphor for gravity. The little ball didn't feel a force. It didn't decide to change direction. It's just following the geometry dictated by the shape of the fabric. Same with planets. Same with rays of light. Same with you. Every morning when you take a step, you move along your natural trajectory. And if something deflects you, maybe you're just walking across the bent floor of the universe, stars, planets, black holes, even you. We're not just inhabitants of space, we're shapers of it. Every mass makes a dent, every motion follows a curve. Sometimes people ask, but space is three-dimensional. Why do we draw trampolines? That's flat. The answer is simple. Yes, the analogy is incomplete. Real space has volume, but the principle holds. No matter how many dimensions you live in, if the fabric is curved, motion within it will change. And gravity is born right there. It's not just a helpful picture, it's a working model. Scientists use it to calculate satellite orbits, to predict planetary motion, even to detect gravitational waves. Ripples in that same fabric that once gave shape to stars. Chapter 11. Even light follows the curve. Light. We think of it as the most straightforward thing there is. It doesn't hesitate, wander, or debate. It just goes, in a straight line. That seems obvious. But what if the straight line itself has changed? In curved space-time, what was once straight can become bent, and even light has to obey. Imagine a mountain stream. It rushes downhill, taking the shortest route. But if a rock lies in its way, the water flows around it. Not because it's resisting, but because it follows the shape of the land. Light does the same. It travels the shortest possible path. But if space is curved, that shortest line bends too. Near massive objects, stars, planets, black holes, light rays can deviate. Not because something pulls them, but because space-time is curved there. Einstein predicted this, boldly, long before anyone observed it. He said, if a star's light passes near something massive, like the sun, it will bend, and the star will appear slightly out of place in the sky. In 1919, during a total solar eclipse, astronomers tested this. Normally, stars aren't visible during the day. The sun is too bright. But during an eclipse, the sun becomes a dark circle, and around it, stars appear. And sure enough, those stars were shifted. Their positions didn't match where they usually are. Why? Because as their light passed near the sun, it bent. This was the first direct confirmation. Gravity doesn't just pull, it reshapes the very thing light moves through. And so, Einstein was right. Space and time really do bend, and light, once thought to be the eternal straight arrow, bends with them. This was the birth of a new kind of physics. A physics where even light curves around mass, where geometry became an active player in the universe, and empty space stopped being neutral. Chapter 12. GPS doesn't work without the theory of relativity. Every day we pick up our phones, we open a map, we wait for that little dot to appear. You are here, and there it is, precise, within a meter. It tells you which side of the street you're on, which alley to turn into, where to park. We take this for granted, like air, like electricity. But few realize none of this works without one simple idea from Einstein. Time flows differently in different places. The GPS system is a network of satellites. They orbit the Earth at about 20,000 kilometers above the surface, moving at roughly 14,000 kilometers per hour. Each satellite has its own clock, perfectly calibrated. Those clocks tell your phone where you are by measuring how long the signal takes to reach you. But here's the twist. These satellites are in a different frame of reference. First, they're moving. And as we already know, motion slows down time by a few microseconds, seems negligible. But second, they're far from Earth, which means they're in a weaker gravitational field, and the weaker the gravity, the faster time flows. This is a result of general relativity, not just special. So now you have a paradox. Because of motion, the satellite's clocks tick slower, but because of altitude, they tick faster. Both effects are real, and neither can be ignored. In total, the clocks run slightly off, but consistently so. If uncorrected, GPS navigation would be off by several kilometers per day, constantly, unavoidably. That's why, when engineers built the GPS system, they directly included Einstein's equations right into the code. Without them, the whole thing would collapse. So here's the strange reality. Every time you call a cab, follow GPS in an unfamiliar city, or check your location, you're relying on the fact that space and time are flexible. You're not just carrying a phone with a satellite antenna. You're carrying a living reminder that the universe is not as rigid as school textbooks once made it seem. You're using a theory that once sounded insane. A theory that said, time isn't uniform, space isn't fixed, gravity isn't a force, it's a bend. So next time you're out, coffee in one hand, GPS in the other, remember, you are living inside that theory. And maybe, if relativity ever feels too abstract or distant, just open a map and realize, without it, you wouldn't be where you are. Chapter 13: Black Holes and Frozen Time. Up until now, we've talked about gentle curves, about dimples in space-time made by planets, about paths that bend slightly. But now, we look at what happens when space-time can no longer hold together. Imagine a sheet of fabric. You place a marble on it. It dips. You add more weight, the dip deepens, and at some point it collapses. No longer a dent. Now, a hole. That's what happens when mass becomes extreme, when a star at the end of its life collapses into itself. No force can hold it up anymore, and it becomes what we call a black hole. But a black hole isn't an object like a planet. It has no surface, no boundary in the usual sense, just one thing: the event horizon, the edge beyond which nothing returns. Not ships, not probes, not even light. And here, something very strange begins. If you approached a black hole, slowly, carefully, you'd notice the world around you speed up. Light from distant stars would compress into flashes. Clocks on Earth, tick, 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 would race ahead. Everything accelerates, like fast-forwarding a movie. But you slow down. With each step, slower movement, slower breath, slower thought, until the moment you reach the event horizon, and time stops. You freeze, forever. To an outside observer, you appear stuck at the edge, not falling in, not disappearing, just suspended. But to you, you cross the threshold without noticing the moment it became irreversible. What happens next, no one knows. Because everything that enters vanishes from our universe, not because it's broken, but because all motion is now turned inward. Even time itself flows in only one direction, toward the center. We don't see black holes directly, but we see their effects: stars suddenly gone, light bending around emptiness, gas twisted and heated to millions of degrees, flashing one last time before it falls. This isn't fiction. This is real. Such holes spin at the centers of galaxies. One of them lies at the center of ours. You can't escape it. You can't look inside, but you can understand. This is a place where time loses its meaning, where the fabric of space-time tears, where straight becomes a spiral and all paths lead inward. And all of it from one simple truth: mass bends space. Chapter 14. So, what have we learned? It all started simply. A train rushing past a platform, a cup of coffee resting in the carriage, a flashlight pointing forward. Ordinary things. We had no idea that inside them was a doorway into another universe. We learned that motion doesn't exist on its own. It's always relative to someone else. There's no such thing as absolute rest. Everyone is moving, always. It's just that some are moving relative to us. Then came light, stubborn, constant, unyielding. It doesn't follow the rules of adding speeds. It doesn't care whether you're moving or still. Light is the same for everyone. And to make that possible, the universe makes a compromise. It doesn't change the light. It changes time and space. We saw that time can slow down, that moving clocks tick slower, that for one brother years can pass, while for the other just moments. We saw that space can contract, that length isn't fixed, that distance can depend on how fast you move. We learned that gravity isn't a force in the usual sense, it's a shape. Mass bends the fabric of reality, and everything around simply follows those curves, even light, even us. And all of this is not metaphor, not philosophy, not poetry. It's physics, precise, measurable, working. It guides ships, it corrects satellites, it shows itself in eclipses. It predicted black holes before we ever saw them. Now we know time and space are not a stage. They are actors, not the background, but the material itself. They can stretch, they can curve, they can slow down, they can shrink. And the strangest part, we influence them with our motion, with our presence, with our mass. You don't just live in space and time. You are part of space-time. You are made of it. And maybe the most amazing thing is not that the universe is so flexible, but that we figured it out. Chapter 15. A Final Thought. Now you know a bit more about trains, flashlights, and twins, about light that doesn't speed up, about time that doesn't hurry, about space that can bend. You know that gravity isn't a force, it's a turn. That mass reshapes the world, that motion alters the flow of time. You know that the universe isn't a rigid construction, but a flexible fabric that responds to touch. But with this knowledge comes not omniscience, but a quiet acceptance that much will remain unknown. There are places where light cannot reach, moments where time has stopped. You can understand how a black hole works, but you can't look inside. You can predict the ticking of clocks, but you can't stop them. And in that, there is beauty. Because science doesn't destroy mystery, it teaches us how to look deeper. Every theory is not an end, but a new way to ask questions. And beyond the event horizon, there is always another horizon. Beyond what we understand, there is room for understanding of a different kind. And maybe the most human thing is not that we found answers, but that we searched. We asked, we doubted, and we weren't afraid to admit. We live in a world where even straight lines sometimes bend. Thank you for making it to the end. Maybe now, you don't just see streets and lamplight, but what lies beneath them. The fabric, the one everything is made of, including us.